This afternoon session with a talk from Stefan Sommer on, well, this long title.
Did not read it?
There's no question in the title. Looks like there is an answer in the talk.
Okay, so I can explain the title while I introduce the talk. So I'll try to at least attempt to take over from where Alexis' talk and give a more statistical perspective on the diffusion processes or the stochastic EPDIF, and also elaborate a bit on what Sarang told about Tuesday, I think, on maximum likelihood estimation and this diffusion bridge simulation scheme. So Sarang used it for Brownian motion on landmarks, and we will see it here appearing in the context of the stochastic EPDIF equation that Alexis talked about, and also in a slightly different setting. Okay, so just to get the context right, this talk is about statistics on manifolds. So the data here are manifold valued, and I'm like much of my work is inspired by shape analysis. So let's say we have the shape of corpora callosa as Alexis had, and we like to do some statistical analysis, find the mean, find the major modes of variations, do sort of a PCA-like plot like this, and analyze the shapes. Okay, so a typical data set would look like what we see here. Those are actually the 50 corpus callosum shapes that Alexis also showed you. There's some overlap here, you can tell. And okay, so here you see sort of a mean shape and a connection between an observation and the mean. And we like to be able to do this while the space is obviously nonlinear. So that's one example, but anything here applies also to other kinds of nonlinear spaces, so we can visualize many things on, for example, the sphere. So in this case, we have data on the sphere. We would like to find the mean, and we would like to find some notion of covariance. Okay, so that's this sort of the statistical setup, and when I say estimate a mean, then I really mean to do statistical inference. So given data, we would like to find what is the mean shape, what is some notion of correlation or covariance. And we saw one way of doing this in the last talk. This is exactly the plot that Alexis showed you, and I will show you how to make a similar plot with a different method. But the overall aim is the same, get sort of statistics out of the data in this nonlinear setting.
Just to really get the point here, you consider that what you see will be generated by this stochastic model for just the zero value of the initial momentum, something like that. I mean, you are not shooting in any direction. You say you go from the mean and you just look at the stochastic model.
But actually, we don't assume it as such. But in this case, it's natural. There's no evolution in the data. But if they happen to be longitudinal data, then there would be a momentum as well. But I think in relation to the discussion before, the momentum is not special in that sense. We can estimate that as we can estimate the starting configuration. It's the same sort of a parameter, and Alexis matched up the moments. We will do maximum likelihood.
Can you start over there just?
I'm sure you can catch up. Okay, so why at all look at stochastic processes and do this modeling? So first of all, data has noise, and this is of course sort of obvious, but many of the things that we've seen in computational anatomy and even maybe in statistics or manifold value data that don't really have a good notion of noise. So I like to at least try to sort of approach modeling the data with noise. That's one issue. And okay, so there are some more points here. If we look at, for example, shape progression as in a medical context, the progression of the hippocampus during Alzheimer's disease, then the usual LDDMM way models this as a smooth geodesic. And I think there's no real reason to think that such evolutions for the individual patients should be smooth. So adding some noise here just relaxes this assumption. And also for such models, we like the noise likely to be time continuous, so that sort of deviations from the geodesic trajectory happens throughout time. And then there's also a point in for these nonlinear spaces, then everything actually becomes more natural when you have a stochastic process, because a process is infinitesimal, takes random infinitesimal steps, and this is compatible with geometry that is really defined by infinitesimal constructions. Whereas like more vector space value things, you can take a random vector, but this is not in a nonlinear setting. A random vector is a little bit more random displacement between 2 points is harder to define. Okay, so that's the sort of modeling noise thing. The other thing is that if we have likelihoods of data, then it's sort of natural to do manifold value statistics. So much of what I will talk about here would be sort of work just to get a likelihood. And then we do statistics like we have a family of probability distributions depending on some parameter, theta. And for the examples here, you can think of theta as being the mean and the covariance. Then if there's a fixed measure, then at least in some situations we can write up a density function. And if we have data, here x1 to xn, then the density gives a likelihood. And when we have a likelihood, we can do inference by maximum likelihood. Okay, so that's sort of, I mean, with such families of probability distributions, we can do inference. And to statisticians, this is perhaps saying something which is like you learn that in early statistics courses, but it's not actually that much used in statistics of manifolds. So now comes just a few slides on what is common approaches to doing statistics on manifolds. So the most used descriptor of data is the Fréchet mean, and this is defined as the minimizer. So the mean here is x being the minimizer of the sum of the squared distance to the data. And okay, so this generalizes the Euclidean sample mean, and you can see that it's very much dependent on the distances of the data. There's not so much of a probabilistic model here, it's a metric construction. So if we go a bit higher from, so the mean is a zero-dimensional descriptor. If you want one-dimensional or higher dimensional, then principal geodesic, principal component analysis like procedures appear. For example, the tangent space PCA or PTA procedure. And this is, so the construction is you find the mean, you take the data from the manifold, map it to the tangent space, and do linear PCA. So this is effectively linearizing the nonlinear space. And so from a geometric point of view, it's not so natural. And then there are other constructions like geodesic PCA and one called horizontal PCA. And this is, by the way, Fermi coordinates, as we discussed before. So this is by parallel transport. Okay, so many of such constructions, and they all sort of evolve around trying to do something which is natural in Euclidean space, fitting a linear subspace. Well, on a nonlinear space, this is hard because we seldom have totally geodesic subspaces and so on. So you get these sort of advanced geometric constructions, and well, maybe that's another approach. So there's some constructions that sort of go a little bit away from these squares minimizing the geodesic distance to a more probabilistic viewpoint. And one is the probabilistic principal geodesic analysis, where it's, so for example, here you see a geodesic, and then you assume your data is distributed around the geodesic with some probability distribution. There's also further work where it's a regression model, and here we actually also have a probability distribution. But as soon as, the point here is, as soon as you get a probability distribution, then you don't actually need those advanced constructions of subspaces and so on. You can just fit your data by maximum likelihood. Okay, so here's the point again. If we can have our family of probability distributions, we have the parameters, we write up the density function, then we get the likelihood, and we fit our data with maximum likelihood. Then the only question left is, how do we get these probability distributions? So instead of constructing linear subspaces, I'll construct probability distributions. And I'll do it in, maybe exit. So, okay, which kind of probability distributions do we need? So in Euclidean space, the normal distribution gets us pretty far. So from the normal distribution, you can define the mean. Instead of minimizing the square distances, we can frame it as the maximum likelihood fit to the data under the assumption that data are normally distributed. We could do principal component analysis as a probabilistic version of that, or probabilistic PCA. We can do linear component analysis, get the sample covariance, do regression in sort of the sense that Alexander talked about earlier, and so on. So if we can get something that is close to the Euclidean normal distribution, then we can do many of the Euclidean procedures, but in the non-linear space. Okay, so what are the natural probability distributions on manifolds? There are not actually that many. So one that Sarang also talked about is one that is sometimes called the Riemannian Gaussian distribution, which is a distribution defined by its density from the Riemannian distance. And then there's this normalization factor that comes from the integral of the density function over the manifold. So this is at least sort of defining a density function in the tangent space and then mapping it to the manifold. So another one is the heat kernel, or Brownian motion. And this is the heat equation that Sarang used. And okay, so here are two examples, but if we like to do anything like what I had on the previous slide, do something with covariance, for example, then we need to go further. So in this talk, I will discuss three ways of doing it, all with this aim of just getting a parametric family of probability distributions. And the first one is anisotropic normal distributions, which correspond to heat flows with covariance, so spreading out in more directions than others. And then the stochastic epidiff is sort of the Alexis talk, but with a statistical viewpoint. And then by the end, I will also talk about the group Croatian space setting, as we have heard some talks already about, but using this with the explicit aim of constructing normal distributions with covariance. And this diffusion bridge simulation will appear throughout these different constructions. Okay, so let's come back to the Euclidean normal distribution. We like to generalize it to the manifold setting, and so we can either do the density formulation that gave us the Riemannian normal distribution before, or we could use the heat flow version. So if we focus on the heat flow version, then in Euclidean space we can say that the Gaussian distribution arises as a transition distribution of a stochastic differential equation that you see here. This is a standard Wiener process, and sigma here is a square root of the covariance. So if we want covariance of our normal distribution, we make the diffusion go higher in some directions than others, and then out we get the normal distribution. So can we do this on manifolds? So we have already the heat flow, but the heat flow is isotropic. It spreads out in all directions equally, so there's no notion of covariance. So the aim here would be to do something about this and still keep this sort of infinitesimal definition. We would like something which consists of flows and take small steps, because that's natural in the geometric setting. And so another way of saying this is that we don't want to linearize to the tangent space. And then we like a density function which is smooth, so we can do our maximum likelihood. For example, we would like to avoid issues at the cut locus and so on. Okay, so this will sort of sum up to, if we before took a Gaussian in the tangent space and wrapped it to the manifold, we would like instead to have something which sort of originates from the mean and brings the covariance structure in a continuous way over the manifold. This is where we will try to go. Okay, so again on top you see the Euclidean situation with the diffusion process and the square root covariance appearing here. And the point here is that in Euclidean space, this matrix is constant. Both spatially, it doesn't move as you move around in the space, and it's time constant as well. So if you like to do something similar on the manifold, then we need something which is sort of constant in some way. And the best notion of constancy is parallel transport. So we could imagine defining this matrix at one point and then parallel transporting it. But then immediately we come into the situation that if we take two paths to the same point, so say we start at the mean and go to this data point here, then curvature and holonomy means that we will get a different notion of parallel transport at the point. So there's no sort of notion of stationarity that we had in Euclidean space when we go to the manifold. So if we want something that sort of resembles a Euclidean situation, we have to deal with this fact. Okay, so then one way to do this is to lift the problem from the manifold to the frame bundle. So the frame bundle is a fiber bundle consisting of points on the manifolds and ordered bases for the tangent space at the point. So sort of the sketch here is that the vertical direction here corresponds to keeping the base point fixed and changing the bases, whereas moving on the manifold sort of remove, and then you have to do something about choose how the bases you follow your movement. And the idea now is to lift or to define a stochastic process in the frame bundle and then afterwards map it to the manifold. And this can be done in a natural way. So this is based on a construction for defining Brownian motion that is called the Eels-Ellsworthy-Mallory construction. So actually just defining the normal heat flow or the normal Brownian motion on a manifold is not trivial at all. It's not like you just write up the SDE as an Euclidean space. So there's different ways of doing it, and one is to use this frame bundle construction, actually use the orthonormal frame bundle, and then map a process from Euclidean space via the frame bundle to the manifold. So you have a Brownian motion happening in Euclidean space, then you map the stochastic path to the frame bundle, and this gives a stochastic process in the frame bundle, and then afterwards you throw away the frames to get a process on the manifold. Now this is usually done for orthonormal frames, so living in the orthonormal frame bundle, but we want covariance, so we are going to extend it to non-orthonormal frames, and this is sort of what would carry the diffusion process and make it spread around in directions more than others. Okay, so this process here is called WT. This is the driving process. Then we have UT, which lives in the frame bundle, and then we map it to XT, which is the stochastic process that we're interested in, and then we can take the transition distribution of this one. Okay, so just one slide on what this mapping is actually. So it's a mapping from the path space on the Euclidean space to path on the manifold. So let's say you have a path on Euclidean space here, R2, then it's being mapped to the manifold starting at a fixed starting point, and you have to choose a frame, and then you sort of roll this line here onto the manifold, and at each time you roll a bit, you take your frame and you parallel transport it along with your path. So the vectors that you see here constitute a frame for the tangent space, and they are parallel transported along the path. If you have a straight line here, you get a geodesic on the manifold. Okay, so now comes some frame bundle geometry that makes all this thing work. So we're going to flow in the frame bundle, which means that we have a process on the tangent bundle of the frame bundle, and it turns out there's a notion of horizontality here, which comes from the parallel transport. So a horizontal flow means that you transport your point and your covariance without changing it. And HI is a set of globally defined vector fields on the frame bundle, with I going from 1 to n, the dimensionality of the space. And they sort of tell you, so the I's of these vector fields tell you if you move in the direction of the I's basis vector and also parallel your frame along this direction, what is sort of the overall movement in the frame bundle. Okay, and they are globally defined. This is important. So this means that you can define in a natural way your SDE in the frame bundle. So here there's a summation over I, and this is just a standard Wiener process, the one in the Euclidean space. And these HI's are globally defined, and then sort of this gives you a stochastic movement. So sort of the intuitive idea is that we need some kind of reference frame when we move, and the frame is exactly this reference frame. And so we transport the frame, so we transport our frame of reference. Okay, so well-defined stochastic process, we run it to some fixed time. Then afterwards we use the projection to the manifold to get x, and now our probability distribution is the value at time 1. So let's try to sketch this. So here you have this circle indicates the covariance, and here it's circular, so this is sort of the isotropic situation, and here you get the heat flow. And so the coloring is supposed like sketching the density function. Now if you increase covariance, you stretch things, you get your density function to be elongated. And okay, here's higher covariance, and you see things being more stretched out. I will come back to these curves in a minute. Okay, so so the picture was frame bundle manifold, and it's a diffusion process. So one can actually wonder, do we need the whole frame bundle to do this? And it turns out that the answer is no. You only need to transport symmetric tensors, because I mean covariance is really modeled by symmetric tensors, and you can factorize this construction to the bundle of covariant symmetric 2 tensors, define a similar notion of stochastic process, and map it to manifold. You get the same answer. So okay, so we can reduce the complexity here. And then another observation is, because we are parallel transporting at all times, we cannot reach the entire set of frames. So for example, if we start orthonormal, we will keep orthonormal frames throughout the evolution. So we're not going to spread out in the whole frame bundle, and therefore we define yet a sub-bundle called Q, which is a set of points in the frame bundle that can be reached by paths of this type. Okay, so this has a nice structure. And one can then wonder, when is our diffusion process well defined, or when does it give a smooth density function? And for that we have to take into account the Hermander condition and so on. But under in nice situations, we can show that the density in the frame bundle is smooth and strictly positive and satisfies a heat equation, which you see here. This is like the usual L here is sub-Laplacian. So this is like the usual heat equation, except that it's sub-Riemannian actually. So it spreads out only in the horizontal part of the frame bundle. Okay, so this density function lives on the bundle Q that we can integrate over the fibers, and that gives us our density function on the manifold. That was what we wanted. So what happens? So okay, so it's a diffusion process. It spreads out. So what happens in the small time limit if it only starts? Then for heat flows, we know that the negative log density is a small time limit. In the small time limit gives the squared Riemannian distance, and a similar construction or similar situation happens here. So in the small time limit, our new density function here looks like sort of the PDF of a Euclidean normal distribution, and this distance here is called dq. So this is a distance on the Q bundle, and it's sub-Riemannian, but it's sort of a distance that takes into account the covariance for each step. So you wait when you move, you wait by the covariance of the process, and then we get a similar limit here. Okay, so the overall aim was to do maximum likelihood estimation. So now we have our density function. We can write up the likelihood, and we can minimize it. And if we don't want to compute the actual likelihood, then we can use the small time limit and put in our distance function, and then we get this estimator here, the minimizer of the squared distance to the data, but with the dq distance. So this is actually very much like the Fresnel mean construction, except now our distance is weighted by the covariance. So here you see two examples: data points, stochastic paths, and now we find the minimal, the curve satisfying this distance here, and estimate mean and covariance. Okay, so back to this picture. So let's say our diffusion process starts at the point here, and now we like to find the curve that minimizes the dq distance to a point on the southern hemisphere. So the black curve here is a geodesic, and the blue ones are curves minimizing the distance function. So in the isotropic situation, we get geodesics, and as an isotropy increases, we get something that deviates from geodesics. So you can see here that the curves sort of want to move in the direction that weighted by the covariance are cheap. I think it's quite neat actually that sort of the probabilistic covariance structure of the data interacts with the curvature of the manifold to give you a new set of minimizing curves. And so of course when I define my mean estimator, I use this distance because it sort of takes the covariance into account. Okay, so these are just, so for this, the paths you get out, you can write up an ordinary differential equation, and then you can plot different examples of what do these paths look like. So think of them as sort of anisotropic generalizations of the family of geodesics. And here you see some examples. So they're sort of quite rich in structure actually, and you can get phenomena like this. Okay, so another way to say what they are projections of sub-Riemannian geodesics in this Q bundle to the manifold. But they're way different than geodesics. Okay, so that was one type of yeah.
Since you're changing. For the Brownian motion, you have an interpretation of the random walk where already do some small exponential steps with the proper covariance metric in each time. Can you do it similar? Could you have done it the same way, like in that case at each step you kind of transport your covariance matrix to the next step? Do you find the same result, or is it something different?
So I think it's a similar kind of limit. So actually, when you do it in the frame bundle, then it's an ordinary Brownian motion with this sub-Riemannian metric. So it's not it's really a sub-Riemannian Brownian motion, but it's not scaled in any way. So I think any sort of result on Brownian random walks would hold in the bundle, and then okay, you map them to the manifold, then it would be fine. Okay, so that was the first sort of view, how to construct normal distributions with covariance. So now we take a jump. So this is the stochastic EPDIF process that Alexis showed us before lunch, in the general form up here with the reconstruction equation, and in the landmark case down here. So again, the aim is we have our data set of corpora colosa, and we like to do some inference, find the mean, find out something about the covariance structure. So the idea here now is to, so we can look at the stochastic EPDIF as sort of in a fluid-like formulation. We have a general flow and perturbations on top, but we could also view it as just a sort of a vehicle to get a probability distribution on the space of landmarks in this case, or the space of curves or images or whatever. So like with this view, then we have a probability distribution, and we like to do inference just as in the previous case. So let's say we have observations, and now observations will be in the form of landmark configurations at some given time. So we assume data are distributed with this process, and we like to see them at some point, and we aim to find parameters. So the setting is exactly as Alexis explained us. And there's two ways of doing it. One is matching the moments, and so we already saw this. And the other one is to do it in a more Monte Carlo approach, to expectation maximization and simulate from the stochastic process. So in EM, you have this Q function that is expectation over the data, or actually the model condition on the data. So we condition on our observations, and then we take the log likelihood and take expectation over this, and we iterate by doing this expectation and then taking a gradient step, or maximizing Q with respect to our parameters. So central for this is to take this expectation. So we are sort of in a missing data situation, because we assume our data is distributed according to the stochastic process, but we only observe at one time point. So we don't know what is the stochastic trajectory until the time point. And we like, so this, in order to do this estimate or the expectation here, we have to take this into account. And we're not going to solve this expectation in closed form. So what can we do? We can do Monte Carlo simulation. So now for each data point qi, we're going to sample a number of samples from the process and then compute the log density or the log likelihood and then sum that up, average it, and then we approximate our expectation. So in order to do this, we need to sample from these from the process condition on hitting the data point, or in another way to say this, that we need to sample bridges for the process to the data point. So this is the same situation as what Sarang discussed Tuesday. And the approach is the same, but we will see it in a slightly different setting. So let's just repeat what was the Euclidean construction that sort of inspired it. So let's take a general Euclidean diffusion process with drift and diffusion field. And then Didion and Hu from the 2006 paper showed us we can simulate from the drift process by adding this term here that sort of attracts us to the point we want to hit, which is V. And it's as t approaches capital T, the end sign, we increase the weight on the forcing term. Okay, so this process will hit V almost surely, and under some conditions on B and sigma. And then we can write up the expectation over the condition process is equal to the expectation over the new process weighted by a correction factor, which is given on this explicit form. Okay, so if we can compute this correction factor, we can sample from Y and use that to get the expectation over X. This is exactly what we wanted. So here's an example for doing it on landmarks with the stochastic EPDIF process. So we start from a configuration with the X's here. We like to hit the green points here. We like to hit the blue points, and the green points are the value of the guided process at time t 1/2. So, and these arrows here are the guidance function, the drift that we add to the model. Okay, so it actually works and gives us a bridge, but it has this problem that I think, Long, you asked about for Sarang's talk, that these bridges are actually very improbable. So we sort of are in the situation that our guidance term, so the guidance term sort of attracts us to the points too fast, and this is a consequence of the high drift that we have in the model where there's a momentum. So as soon as there's initial momentum, the landmarks move a lot, and then if we guide in this setting with just taking the difference, we're going to pull way too hard towards the target and get improbable bridges. So we cannot use this method in this out of the box. Okay, so what do we do? So there's this problem about the too high drift, and then we also have to modify it because our process, which now lives on the whole phase space Q and P, is not elliptic, it's subelliptic. Basically, we can assume that we know that it fills up the Q space with noise, but we cannot say anything about what happens for the momentum. Okay, so with some work on the analysis, we can get around this because we only observe the landmarks in the Q space. We only observe the configurations and don't care about the momentum. So that's one issue, and then the other thing is about this drift term being too high. So the final process that we are using is displayed here, and here's V, and now instead of just guiding from the current value of the process, we apply a function to it. And this function is equal to, or approximately equal to, the expectation of the value of the process at time capital T given the current value at time t. So we're sort of seeing like where do we end in expectation given where we are now. And then this was a plot we saw before, becomes much nicer halfway through time. We are here and sort of halfway where we should go. And you can also see it more exaggerated on this plot. So at this point, we use the phi function to see where we are going in expectation. That's this point here. And then we guide only by the slight difference between the target and the point where we are, the phi point. Okay, so that reduces the drift. We still hit, and we get more probable bridges. And okay, so putting all this into the framework, we can simulate the bridges, compute the correction factor, compute the likelihood, and put it into an automatic differentiation framework. We use Ciano, but we heard about PyTorch Monday, and I guess they have sort of a similar functionality. Take gradients with respect to the initial parameters because we like to do maximum likelihood, and run the machinery, and now we get a plot like this, which is at least sort of similar to what Alexis got. Okay, so that was the stochastic epidiff and bridges. So now I just want to end by giving some like a brief overview of how this can be done also in more general manifolds and D group. So let's say we have a manifold or a group. I'll focus on group, so I call it G. And we have a stochastic process. Now it's not the stochastic epidiff, but any kind of process. And we like to guide it in the Delian who sense towards a target V. So this is the Euclidean bridge. And a point is that we could use this directly in the landmark situation because the landmark manifold has a global chart. So the landmark manifold is nonlinear, but it's we have a global chart on Rn, so we can just use the Euclidean distance. But if we like to do it in more general on a manifold, then we don't have global charts, so we need to do something different. And the obvious thing is to take the same sort of construction and but use the guidance here to be the Riemannian logarithm map from the current position at time t to the target point. So if we could write up this process, then we could guide, and I guess it would work, but the problem is we cannot because this logarithm map is not continuous as soon as we hit the cut locus of the manifold. And for this SDE series to work, we need things to be Lipschitz and so on, so there's no direct way to do it. Okay, so I'll just sketch sort of a construction. This is something that that we've been working on over just a few weeks back, so it's sort of recent and not completely finalized work. But the way to approach it is to look at this process here, which is the exact bridge process. So Sarang also displays this one. So here's also an added drift term, but it's not coming from this y minus v divided by t minus capital T minus t. It's coming from the gradient of the actual density function. So this gives us the exact bridge process, but it's completely useless for simulations because we don't know p. So there's no way we are going to use this gradient. Okay, but we'll anyway use this bridge process for comparison. So the idea now is to make our new process that we guide with, take a gradient of a function, and this function should be like what we had before. So the gradient of the squared distance is exactly this logarithm that I had on the previous slide. And we'll use this one except near the cut locus, where we'll use the one that we know is the correct one, the log density. And so this process will converge, and you can see that by comparing it to the exact bridge process in the same way as in the Delian Hu paper. And then the nice thing is that even though we use this d that depends on the density function, the process will actually not come close to the cut locus with high probability. I think it's actually almost surely, but that's not completely clear yet. So in practice, when we sample, we can use the log anyway, even though the analysis uses the actual density function. Okay, so how does this look like? So here I show you two processes and the situation is you have SO3 and you quotient out S2 to get the sphere. So here is the D group, and here you see the quotient space manifold. And the Lie group pictures that you have a basis in R3, and you let the process modify the basis. And this is a Brownian motion with respect to some metric chosen on the group, simulated forward in time, but now we condition on hitting a point. And you can see that by both processes here hitting the same point. So 2 realizations of the same process guided by this guidance term, and then, okay, you get your bridges, you can compute your correction factor and take expectation again. And so what is the sort of or more general motivation for doing it in this setting? Well, if we run such a Brownian motion on the group with respect to an arbitrary metric, then we can push down to the quotient and see what we get. And it's, if the metric on top is bi-invariant, then the Brownian motion will be projected down to a Brownian motion, and what you will see is some sort of Gaussian-like density coming from the heat flow. But if it's not invariant on D, then what you see is something like this. You see a Gaussian-like distribution with covariance. So the upshot is sort of from this quotient space construction, you're able to generate yet another way of yet another normal distribution like construction with covariance. Okay, so in a sense, what the bigger picture is that before we had to use a frame bundle to keep track of the reference frame as the process evolves, but now in the group situation we can use the Lie algebra of the group to keep track of the Brownian motion and then push that down. So before we had the manifold as the quotient and the frame bundle as a fiber, now we have the quotient space as the quotient, and we have the frame bundle for the stochastic process. Okay, and so this is a simulation from the bridges to evaluate the density function. And again, so all of this, I mean, just in any way to be able to compute this, we need automatic differentiation. So the steps are that we have an SDE and a discrete sampler for the integration scheme for the SDE. Then we add these guidance terms, compute the correction factor, take expectation, and then afterwards we take derivatives for the parameters of the model, right? The metric. So if you were to write this up by hand, it would explode. But yeah, automatic differentiation, that's really nice. Okay, so just to conclude, the overall message was to enable statistics on manifold via maximum likelihood estimation, and for that we need these different kinds of probability distributions. For the normal-like distributions, we saw the interaction between covariance and curvature and the family of anisotropic geodesics. For the epidiff, we also got a probability distribution that we could use, and then we have the bridge sampling both for the epidiff and on the V group, and this sort of anisotropic normal-like distribution on quotient spaces. Okay, so I'd like to stop here and say thank you for listening.
You have the term inference in your title, so with the MLEs you would like to do something more, right? You would like to maybe have bands and you want to quantify your uncertainty, like, go beyond just the estimation. The classical theory, there's a lot of nice stuff which happens with MLEs. Can you comment on whether you have something?
So beyond
estimation, you want to do inference, maybe you want to do some testing, maybe you want to do...
Yeah, I mean, so anything you could do from having a density function and a likelihood, I think likelihood ratio tests and things like this would be possible. But yeah, so what I've done so far is just to find means and covariance and correlation structure and so on. But you're right, this would definitely.
My question is whether, so the properties of the MLEs in the classical setting is it has all these nice properties, asymptotic properties and so on, which is used eventually for likelihood ratio tests and so on. Do you have any sense of what you might expect in this setting with the MLEs you obtain from?
No, we haven't done any analysis on asymptotics, but okay, there are some on. So, for example, for the Fresnel mean, you have asymptotic estimates of the convergence of the sample Fresnel mean to the actual one, and I think for the maximum likelihood mean, there are similar. I'm not sure if it actually has been done, but it's not too different for the maximum likelihood mean that you get with this Brownian motion construction. But I mean, it's not something we have worked on, so that's open.
So can I make a remark? About Brownian motion and Laplacian operators. When we actually specialize to the EPDIF, right, or one of its finite dimensional versions, what we get when we're looking at pocket clocks is not Laplacian, right? We get the double Lie derivative instead. And if the medium, if the surface on which you're looking for the diffusion is Riemannian manifold, then this double Lie derivative is related to the Laplacian, but it's not the Laplacian. So it seems like if you're going to adapt, to motion that's generated by the Lie algebra, that your diffusion operator would change. And it changes in a nice way. On a manifold, the double Lie derivative is basically the sum of the Laplacian and this half the trace of the Ricci tensor. So it'd be an interesting thing to look at. So it's like an adapted Brownian motion.
Yeah.
Have you seen that?
No, it's not something that I've seen, but you're right.
Peter, you know about this, right?
Yes. Yeah, you can. Oh, sorry.
No, I want to escape. Now, when you presented the last, the general setting where you want to have this guided diffusion, general homogeneous space, I think. At some point you have the distance. It can be any distance because, to have this guided thing, you have to compute the distance to the target and to compute the gradient and so on. So in a sense, I think in a real situation, it will be as costly as computing the geodesic distance. So I think you could, in fact, it's not. I just wanted to know if, in fact, you can use any distance, maybe not the real geodesic distance, but you just need to be able to compute the correction factor.
Yeah. So for example, one idea would be to use the embedding space distance.
Yeah.
And project it to the.
Yeah.
And
what you are doing. Okay.
Yeah, so I cannot really give you a perfect answer to it. So I think I think this can be done, but I think you have to somehow control the process. So then you get a different process, right? Because you're guiding by something different. Right now I'm guiding with this logarithm, and if you guide by different distance function, you get a different process that you sample from. And you have, if you're going to prove, so it definitely works numerically, then it's nice, but you have to prove also that it doesn't blow up, for example. If the distance vanishes, or the gradient of the distance vanishes, then...
So it can be correct.
Yeah, and so I think either it just works, or what you have to do is say that as long as you are sufficiently close to a target point, you use the nice, easily to compute distance, and if you get close to, say, the Cold-Locus, you use the actual Riemannian distance. So you can sort of weigh between them, and then in practice, you will never get close to the critical points. Okay, so maybe, I mean, there's some analytical questions, but in practice, you can use any distance.
Okay, thank you.